Welcome to Wisdom Docs. Tonight, there is nowhere you need to be and nothing you need to solve. You can let your shoulders drop away from your ears. You can let the weight of the day settle out of your hands. Wherever you are right now, in whatever bed or chair has caught you at the end of this long turning of the earth, you are exactly where you are meant to be, and you are allowed to simply rest here while I tell you a slow and strange and true story about the ground beneath us all. Picture, if you can, a quiet hillside on Vancouver Island. It is an ordinary place. There are cedars and Douglas firs holding still in the dark, and somewhere down the slope the cold grey water of the strait laps at the shore the way it has lapped for 10,000 years. On that hillside, bolted to a slab of concrete sunk into the bedrock, there stands a small instrument, a continuous GPS receiver, no larger than a dinner plate, tilted up at the sky. It does nothing dramatic. It does not hum or flash. It simply listens every second of every day to a chorus of satellites passing far overhead, and from that endless quiet conversation, it works out, again and again, exactly where on the surface of the planet it is standing. Not roughly, not approximately, to within a few millimeters, to within the width of a few grains of rice laid side by side. And here is the first strange thing, the thing that should not be possible, the thing that a small handful of people came to understand only at the very end of the last century. That little receiver on the hillside is not standing still. None of them are. The whole western edge of the continent is moving slowly, patiently, all the time, and the instruments can see it move. Year after year, the ground beneath Vancouver Island creeps eastward, inland, toward the heart of the continent, a few millimeters at a time, pressed and dragged by something enormous happening far below. You would never feel it. You could lie down on that hillside for your entire life and never sense the faintest shift, but the receiver feels it. The receiver draws a line, a long, steady, climbing line on a chart, the slow signature of a coastline being squeezed. And then one day, the line bent the wrong way. For weeks, with no warning, on no fault that anyone could see, the ground on Vancouver Island slid backwards, not forward, inland, the way it had crept for all the years before. Backwards, seaward, westward, out toward the ocean, as though the land had taken a long, slow, reluctant breath and let a little of it go. A centimetre, perhaps two, over the course of 2 or 3 weeks. An amount so small that if it had happened to a tabletop, you would not notice it had moved at all. And yet it was there, plain and undeniable, a kink in that climbing line, a place where the steady creep of a continent simply paused, reversed, drifted back the other way, and then, after a few weeks, returned to its old direction as if nothing had happened. No one felt it. Not one person standing on top of it felt a single thing. There was no rumble, no jolt, no rattle of windows, no dish slipping from a shelf, no dog suddenly awake and barking at the floor. The birds did not scatter. The water in the glass on the bedside table did not so much as tremble. And yet, in those quiet weeks beneath the cedars and the firs and the sleeping towns, an earthquake had taken place. A real one. 2 great plates of the Earth's crust had slipped past one another, the same kind of slip that, when it happens in seconds, tears cities to the ground. Only this slip did not take seconds, it took weeks. And because it was so slow, so unhurried, so impossibly gentle for something so vast, it released its energy not in one violent shock, but in a long, soft exhale spread out over many days. And so it shook nothing at all. A magnitude 7's worth of energy, released over 3 weeks, felt by no one. Let that sit with you a moment, the way you might let a warm cup sit in your hands before you drink from it. The energy of a great earthquake, the kind of earthquake that on any other day, in any other place, would level buildings and crack roads and write itself into history with rubble and grief. That same colossal quantity of energy moving silently through the rock, slipping out over the span of half a month, so smoothly and so slowly that the people living and working and sleeping directly above it carried on with their ordinary lives entirely unaware. They drove to work. They cooked their dinners. They put their children to bed. And all the while, beneath their feet, an earthquake the size of a disaster was unspooling at the pace of a tide going out. And not one of them ever knew. This is what we are going to wander into tonight slowly, the way you might walk down into a deep cellar by lamplight, one cool step at a time. We are going to follow the trail of a kind of earthquake that no one can feel. And it is, I promise you, a story to sink into rather than a story to be startled by. There are no jump scares here, nothing that will jolt you awake. The whole point of these silent quakes is their slowness, and we are going to honor that slowness all the way down. But before we go any deeper, let me say something simple and true. Nobody fully knows what these silent earthquakes are. Nobody can say for certain why some patches of fault choose to slip slowly and silently, while others, just above them, stay locked and rigid for centuries until they snap. And nobody can yet tell you with confidence whether each of these quiet slips is bringing the next great catastrophe a little closer, or whether it is, in some patient way, holding it at bay. Who? When? Why? The honest answer, even now, even with all our satellites and our buried instruments, is that we are still standing at the edge of the mystery, holding up a small light, watching the ground move in ways we have only just learned to see. And that is part of why I find it so strangely restful. There is something in the not knowing that softens the whole thing. We will get to what we do understand, and we understand a surprising amount. But the great unanswered question hangs over all of it like the dark over a valley, and you are welcome to drift off somewhere inside that dark without feeling you have missed the ending. There may not be a tidy ending, there rarely is with the deep earth. If it feels right to you, I would love to know where in the world you are listening from tonight. Some of you are tucked into long winter nights, with frost feathering the corners of the windows. Some of you are in the thick, warm dark of a summer that won't quite cool down. Leave a word in the comments if you like, the name of your town, your country, the view from your window. I read them. And there is something quietly lovely about imagining all of you scattered across the whole spinning surface of this planet, all of you resting above the same restless rock. And if you are new here, and you would like more of these slow journeys into the strange and the true, you might gently tap the button to subscribe so the next one finds its way to you on some other tired night. That is the only thing I will ask of you. After this, there is nothing more to do but listen and let go. So, settle in, find the warm hollow of the pillow, let the lamp burn low. We are going down into the rock now, slowly, slowly, all the way to where the silent earthquakes live. To understand what slid backwards on that hillside, you first have to understand where it slid. And to understand that, we have to go to the western edge of North America, to a long, hidden seam in the planet that has a name, though most of the people living on top of it could not tell you what it is. It is called the Cascadia Subduction Zone, and it is enormous. Imagine the coastline of the Pacific Northwest. Begin in the redwood country of Northern California and run your eye up the map, north and north and north, past the long beaches of Oregon, past the mouth of the Columbia River, up along the green misted shores of Washington, past the city of Seattle drowsing beside its sound, and onward still, up past Vancouver and across the strait to the island, all the way into the cold waters of British Columbia. That entire stretch of coast, roughly 1,000 kilometers of it, an unbroken line longer than many countries, sits on top of one of the most powerful geological machines on Earth. A place where, just offshore, beneath the grey and heaving Pacific, one piece of the planet is sliding slowly and inexorably underneath another. Out there, beneath the waves, lies a slab of oceanic crust. It does not have a grand or familiar name. It is called the Juan de Fuca Plate, and tucked beneath the southern end, off the coast of Northern California, there is a smaller fragment of it called the Gorda Plate. These are not the great famous plates you may have heard of. They are modest in size, almost overshadowed the leftover pieces of a much larger ocean floor that has, over tens of millions of years, almost entirely vanished beneath the continent. And that word, beneath, is the whole story. Because the Juan de Fuca Plate is not simply bumping up against North America at the shoreline, it is diving under it. The heavy, dense rock of the ocean floor is bending downward at the coast and sliding underneath the lighter rock of the continent, descending at a shallow angle, going down and inland, deeper and deeper, until it disappears far below the mountains and is swallowed into the hot interior of the Earth. This is what the word subduction means, one plate ducking beneath another. A slow, ceaseless, grinding submersion that has been going on in one form or another for longer than there have been human beings to stand on the shore and watch the sea. Now, in a perfect and frictionless world, that diving plate would slide smoothly down and under, and the surface above would feel nothing at all. But the world is not frictionless. Where the two plates meet, along that vast, tilted seam, the rock is not slick. It is rough. It catches, it sticks. And here is where the danger lives, the slow, building danger that the whole rest of our story circles back toward, like water finding the lowest ground. Across a wide band of that interface, the part that is not too shallow and not too deep, the part where the rock is cold and brittle and strong, the two plates are not sliding at all. They are stuck, locked together, welded by friction and pressure, holding fast, refusing to move. But the plate behind them does not stop. Out in the ocean, far from the coast, the Juan de Fuca Plate keeps pushing inland at its steady few centimeters a year, the pace, more or less, at which your fingernails grow. It pushes and pushes and pushes, year after year, century after century. And because the seam at the coast is locked, that relentless push has nowhere to go. So it builds. The rock bends. The continent's edge is dragged downward and squeezed, compressed like a spring, being slowly, slowly wound. Strain accumulates in the stone, year upon year, decade upon decade, an invisible reservoir of stored force growing quietly beneath the beaches and the forests and the sleeping cities with no way to escape. That is what the GPS receiver on the hillside was measuring all those years it drew its steady climbing line. The slow inland creep it recorded was the sound of the spring being wound. The land was being dragged eastward because the stuck plate beneath it was dragging it there, hauling the surface along as it strained against the lock. And so when that line bent backwards, when the ground slid briefly seaward, what the instruments had caught was a moment when some part of that lock, somewhere down in the dark, had loosened, and the bent, strained land had relaxed back toward the sea, just a little, just for a few weeks, the way a drawn bow eases when you let a breath of tension out of the string. But understand what kind of place this is, and what it is capable of when the lock fails not gently, over weeks, but all at once. Because a fault that can store 1,000 kilometers worth of strain does not, when it finally breaks, produce an ordinary earthquake. When the locked zone of a great subduction seam like Cascadia lets go in a single violent rupture, it produces one of the largest earthquakes the Earth can make. A megathrust earthquake. A magnitude 9. a shock so vast it is hard to hold in the mind, hundreds of times more powerful than the quakes that have leveled cities in living memory, a tearing of the seabed that lasts not seconds but minutes, that drops whole coastlines downward in an instant and shoves the ocean into a wall of water that races outward across the entire Pacific. Cascadia can do this. Cascadia has done this, and it is, even now as you lie there, breathing slowly in the dark, winding itself up to do it again. We know it can because we know it has. And here is one of the most quietly astonishing pieces of detective work in all of Earth science, a story worth slowing down for, because it shows you how the deep past can be read out of the smallest and strangest of clues. For a long time, the people studying the Pacific Northwest coast suspected that Cascadia was dangerous, but they could not prove it had ever produced a great earthquake. There were no written records. The peoples who had lived along that coast for thousands of years carried oral histories of a terrible shaking and a great flood passed down through generations, but the newcomers who came to study the rocks wanted something they could pin to a date, and the coast itself held a clue if you knew how to read it. All along the shores of Washington and Oregon, in the tidal marshes and the river mouths, there are places where you can find the remains of dead forests. Ghost forests, the grey, bare, salt-killed stumps and snags of great cedar and spruce trees, standing or lying where they fell, rooted in soil that is now below the reach of the tides. These trees did not die slowly. They died because the ground they stood on dropped, suddenly all at once, lurching downward by a meter or more and pulling their living roots down into the salt water, drowning them where they stood. That sudden drop is the signature of a mega-thrust earthquake. When the locked seam ruptures, the strained, lifted edge of the continent springs and then settles, and great stretches of coastline subside, dropping into the sea in a single violent moment. So the ghost forests were proof that it had happened. But when? The wood gave a rough answer. The growth rings in the dead trees showed they had all stopped growing at the same time, in the same year, sometime around the turn of the 18th century. But around the turn of the 18th century is not a date, it is a guess. And the story might have rested there, frustratingly vague, were it not for a record kept on the far side of the entire ocean by people who had no idea that a continent had just torn loose 4,000 miles away. Across the Pacific, in Japan, there were villages along the coast that had kept careful written records for centuries, records of harvests, of taxes, of weather, and, crucially, of the sea. The Japanese coast knew tsunamis well. Almost always a tsunami there was preceded by an earthquake. The ground would shake, and then, some time later, the wave would come, and so the people understood the two as bound together, the shaking and the water, cause and consequence. But buried in those old records there was a strange and troubling entry, a description of a tsunami that had arrived with no earthquake at all, a wave that came rolling in out of the Pacific in the dead of night, flooding fields and damaging houses and frightening the villagers with no shaking before it, no warning, no felt cause, anywhere in Japan. An orphan tsunami, a great wave with no parent quake that anyone in Japan had felt. A child of some catastrophe that had happened too far away to be felt at all, sending only its water across the breadth of the ocean. And because those Japanese records were so meticulous, the orphan wave was dated not just to a year, but very nearly to an hour. It arrived in the night. And when scientists much later sat down and worked backward, measuring how long a tsunami takes to cross the Pacific from the Cascadia coast to Japan, and matching the drowned ghost forests of Washington and Oregon to the timing of that fatherless wave on the other side of the world, the two halves of the puzzle clicked together with a precision that still gives me a chill of wonder when I think of it. The last great Cascadia earthquake, the rupture that dropped the coastline and killed the forests, struck on the evening of January 26th in the year 1700 at roughly 9 o'clock at night. 300 years ago and more, a single evening in the dead of a North American winter, the ground heaving in the dark, the coast dropping into the sea, the forests beginning to drown, and a wall of water setting out silently across the entire Pacific Ocean, to arrive a day later on the shores of villages who would write it down without ever knowing what had caused it, so faithfully that we could read the answer out of their words 3 centuries on. The ghost forests and the orphan tsunami, 2 whispers from opposite ends of the largest ocean on Earth, fitting together into a single date. The 26th of January, 1700, around 9 in the evening. And here is the part that should settle over you slowly like a quilt drawn up in the cold. That was the last one. Since that winter night in 1700, the great locked seam of Cascadia has not let go. For more than 300 years now, the Juan de Fuca plate has gone on pushing inland at the pace of a growing fingernail, and the locked zone has gone on holding fast, and the strain has gone on building, quietly, invisibly, year after year after year, beneath the cities that have grown up along that coast in the centuries since, beneath the highways and the harbours, the bridges and the schools, beneath all the ordinary sleeping lives that have come and gone above it. 300 years of winding the spring, 300 years of stored force, growing with nowhere to go. It has been silently loading ever since. And that, you see, is why those few centimetres of backwards motion on a quiet hillside meant so much. Because somewhere down in that loaded, straining, locked-up machine, in the deep transition where the rigid rock gives way to the warm and yielding rock below, something had begun to move on its own. Not the great locked seam itself, not the part that will one day spring loose and drown the forests again. Something just beneath it, something deeper and stranger and gentler, that slips when the rest holds firm, that breathes out a little of the strain in long, slow exhales spread over weeks, that has been doing so, we now suspect, all through those 3 silent centuries, returning again and again on a quiet rhythm of its own, entirely unfelt, entirely unseen, until the day we finally built instruments delicate enough to watch it move. For most of the history of the people who study the Earth, this whole hidden process was invisible. It had to be. The slip is too slow to shake, and the tools that were built to catch earthquakes, the seismometers, the trembling needles, and spinning drums designed across more than a century to register the sharp, fast jolt of breaking rock, were, by their very nature, deaf to it. They were built to catch the shout, and this was a whisper. They were tuned to the violent and the sudden, and this was the patient and the slow. An earthquake that takes 3 weeks to happen does not register on an instrument that is listening for the snap of a single second. And so for generation after generation, beneath the feet of everyone who lived along that coast, these silent earthquakes came and went, again and again, magnitude after magnitude of energy slipping quietly out of the rock, and no needle anywhere moved to mark them. They happened in a kind of darkness we had made for ourselves, a blind spot built into the very tools we trusted to tell us what the ground was doing. How many of them, I wonder, rolled silently beneath the towns and the forests in all those years before we could see? How many slow earthquakes came and went under the sleeping coast in the 300 years between the drowning of the forests and the bending of that GPS line? Each one an event the size of a disaster, each one utterly unfelt, each one nudging the great locked seam by some small and patient increment, and not one of them ever recorded, ever known, ever even suspected to exist? We will never have that count. That ledger was never kept. The Earth was writing in an ink we had not yet learned to read. And so the deepest question of all begins to take shape here, in the dark, where we are going to leave it for now to settle and deepen as we descend. If the ground can move without shaking, if an earthquake the size of a catastrophe can unfold over weeks beneath a sleeping city and leave no trace a human being could feel, then what exactly is the relationship between these silent, slow shudders and the great violent rupture that is still, even now, slowly building beneath that 1,000-kilometer coast? Each silent slip eases a little strain from the deep, yes. But each one also, in easing, presses ever so slightly on the locked zone above, the part that is waiting, the part that struck in 1700 and has been loading ever since. So which is it? Is each quiet exhale carrying the great quake a little further off, or drawing it a little nearer? Is the silent earthquake the ground letting go of its tension, or the ground tightening one more notch toward the day it finally breaks? That is the thread we are going to follow slowly and gently down through the rest of this long night. We are going to learn how a small group of people, almost by accident, first caught the ground sliding backwards. We are going to go down to the precise depth where these silent quakes live, into the warm and watery dark between the locked rock and the flowing rock, and see what it is about that one strange band of the fault that lets it slip so slowly and so quietly when everything above it stays rigid and waiting. We are going to find out why the gravitational pull of the moon, the same gentle tug that lifts the tides each day, is enough to switch these silent quakes on and off. And we are going to ask, as honestly as we can, the question everyone wants answered and no one can fully answer: what these quiet shudders are really telling us about the great megaquakes still slowly winding tight beneath Cascadia and beneath Japan and beneath the long stressed coasts of the world. But not yet. Not all at once. For now, it is enough to know that beneath that quiet hillside on Vancouver Island, beneath the cedars holding still in the dark, the ground once slid backwards. An earthquake the size of a disaster slipped silently through the rock over 3 slow weeks and no one felt a thing. And a few hundred kilometers below the surface of an ordinary winter night, in a place we had never thought to look, the earth was breathing. So keep breathing with it, slow and easy, in and out. There is a long way still to go and all the time in the world to get there. The plate is moving at the pace of a growing fingernail. The silent quake unfolds at the speed of an outgoing tide. Nothing in this story is in any hurry at all, and neither are you. Let the slowness of the deep rock become the slowness of your own breath, and we will keep going down gently into the warm dark, where the silent earthquakes are still, even now, quietly coming and going beneath the sleeping world. And the question of how we found them at all is itself a kind of detective story, slow and patient, and built on instruments measuring things so small that the notion of building them at all once seemed almost absurd. Because for most of the 20th century, the Earth's silent earthquakes were happening, rolling through the deep rock on their steady, invisible clock, and the tools humanity had built to listen for them heard absolutely nothing. Not because the tools were poorly made, because they were listening for the wrong thing entirely. A seismometer is a remarkable instrument. At its heart, the principle is old and almost beautifully simple. A heavy mass suspended inside a frame so that when the ground shakes, the frame moves with it, while the mass, by its own inertia, lags behind. And the difference between the two traces a line on paper or sends a signal down a wire. The first practical seismographs were built in the late 19th century, refined through the early decades of the 20th, and by the time of the Cold War they had become instruments of extraordinary sensitivity, capable of catching the faintest whisper of a distant explosion or a small tremor deep beneath a mountain range on the far side of the world. Dense networks of them spread across the globe, reading the planet's seismic pulse continuously, recording every burst of fast ground motion above some threshold of detection. And they worked beautifully for the earthquakes they were built to find. The sudden ruptures, the sharp P-wave arrivals, the rolling surface waves that spread outward from a break in the fault like ripples from a stone dropped in still water. But a seismometer is tuned to speed. It is listening in the most fundamental sense for fast motion. The physics of seismic wave generation means that for a rupture to send a strong wave through the earth, to announce itself at a seismometer 100 kilometers away or 1,000, it must release its energy quickly. The crack must propagate fast enough, the slip must accelerate sharply enough that it shakes the surrounding rock like a struck bell. A fault that slips at the pace of a fingernail growing, or a glacier advancing, or an afternoon shadow creeping across a stone wall. Such a fault loads and releases stress at a rate so slow that it never produces a strong seismic wave at all. It simply moves. The energy radiates in such tiny amounts, spread over such long durations, that any seismometer listening nearby would register only ambient background noise, the microseisms from ocean waves, the faint cultural hum of traffic on distant roads. Nothing coherent, nothing shaped like an earthquake. And so decades of seismogram records from Vancouver Island, from the Olympic Peninsula, from the Nankai coast of Japan, decades of data from faults that were, it would later turn out, slipping silently beneath the monitoring networks every 12 to 14 months. Those records showed nothing out of the ordinary. The planet was keeping its own secrets not because anyone had been careless. It was keeping them because the question of slow motion had simply never been properly asked. To find an earthquake that lasts for weeks, you need an instrument built not for speed, but for patience. Not a tool that listens for sudden shaking, but one that measures where the ground stands precisely, day after day, week after week, and notices when it has quietly moved. And the instrument that could do this was GPS. Global Positioning System satellites were primarily a military technology built by the United States Department of Defense through the 1980s, and by the early 1990s, the civilian scientific community was already finding ways to use the signals the satellites broadcast to measure positions on the Earth's surface with an accuracy that would have seemed impossible to a previous generation. The principle is triangulation from the sky. A receiver on the ground listens to signals from multiple satellites and uses the tiny differences in arrival time to compute where it stands. In everyday use, the kind of GPS in a phone or a car, this gives a position accurate to a few meters, which is good enough to navigate a city street. But scientific GPS using long averaging times and sophisticated error correction techniques that account for the varying speed of the signal through layers of atmosphere can resolve positions to within a few millimeters, not meters, millimeters, the width of a grain of coarse salt. And if you leave a GPS receiver in one place, fixed to bedrock, running continuously, measuring its own position many times a day over months and years, you can watch that position drift. You can watch a tectonic plate move. You can watch the continent creep, in the case of the Pacific Northwest, slowly eastward at the rate that a fingernail grows, something on the order of a centimeter or two every year, as the Juan de Fuca plate drags the overriding North American crust toward its interior. Networks of such instruments began going into the ground in the Pacific Northwest through the 1980s and 1990s. The Pacific Northwest Geodetic Array, HANGA, built a web of continuous GPS stations across Washington and Oregon and British Columbia, each one bolted to bedrock or set on deep concrete piers to isolate it from the seasonal frost heave and surface motion that would otherwise contaminate the signal. Later, the Plate Boundary Observatory would expand and improve on this, adding more stations and more sophisticated receivers across the entire length of the western margin of North America. And the data coming from these stations settled into a pattern anyone could see. The stations were creeping slowly eastward. Year after year, the ground on Vancouver Island and the Olympic Peninsula edged inland in the direction that the subducting Juan de Fuca plate was dragging the continental crust above it. The subduction was loading the crust like a coil spring being wound, and the GPS was watching it wind. This was expected. This was the science behaving exactly as it should. And then sometime in the late 1990s, something unexpected appeared in the records. The eastward creep did not stop. It reversed, not dramatically, not in a way that would shake a building or startle a sleeping cat. The reversal was a matter of centimeters, spread over 2 or 3 weeks, but on a GPS time series plotted over months and years in which the normal eastward drift shows up as a steady diagonal line climbing toward the upper right of the graph. The reversal is unmistakable. The line for a few weeks bends back the other way. The ground that had been slowly advancing toward the interior of the continent briefly, quietly, moved back toward the sea. Then the reversal ended, and the normal drift resumed as if nothing had happened. It is worth sitting with that image for a moment because it is the thing that changes everything. Imagine you have been watching a clock hand, and you have been watching it sweep steadily clockwise for months, reliably, 1 millimeter here, 2 millimeters there, the same patient arc every day. And then one morning the hand, for 2 weeks, runs counterclockwise, not fast, barely perceptibly, but backward, distinctly backward against everything it has been doing. And then it goes clockwise again. That is what the GPS stations on Vancouver Island recorded. The crust, which had been loading under the compression of the subducting Juan de Fuca plate, had for a moment unloaded. Something had slipped. Something under the ground had released some of the accumulated strain and, in doing so, moved the surface above it backward, seaward, for a brief window of weeks. And then the loading resumed, and the plate went back to winding the spring. It was Herb Dragert and his colleagues at the Geological Survey of Canada who were first to see this clearly, to recognize it for what it was, and to publish it. Dragert, working from the Pacific Geoscience Centre in Sydney, British Columbia, had been studying the GPS records from the network of stations across Vancouver Island and the mainland coast, looking at the long-term deformation patterns, trying to understand how the strain from the ongoing Cascadia subduction was being distributed across the crust above the Juan de Fuca plate. What he found in the 1999 data was the reversal. A cluster of GPS stations on Vancouver Island, stations that had been diligently creeping eastward for years, briefly moved westward back toward the ocean over a period of several weeks, then resumed their eastward march as if the interruption had never occurred. The total displacement was small, on the order of a centimeter or two. But centimeters, accumulated as they are over weeks of slow motion, represent an enormous amount of fault slip deep underground. Working backward from the surface displacement, Dragert and his colleagues could estimate how much of the deep fault had moved, how far it had slipped, and what the energy release of that slip amounted to. The answer was sobering in its scale. This quiet, unfelt, invisible reversal of a few centimeters on the surface corresponded to a fault slip at depth equivalent in energy to a magnitude 6.5 earthquake. An earthquake large enough, had it been a normal fast rupture, to crack foundations and ring church bells and knock groceries from shelves. It had done none of those things. It had slipped silently over 3 weeks, released its energy as slowly and gently as a held breath let out, and no one standing on the ground above it had known a thing. Dragert and his co-authors published this in the journal Science in 2001. The paper described a silent slip event beneath the Cascadia subduction zone, a transient aseismic slip on the deep part of the Juan-de-Fuca North America plate interface, and it arrived in a scientific community that was beginning, tentatively, to suspect that such things might exist, but had not yet seen one so clearly documented in a region like Cascadia, a margin known to be capable of the most violent earthquakes on Earth. The 2001 paper did not immediately resolve the question of what had caused the slip, or how regularly it recurred, or whether it was connected to anything else happening on the fault at the same time. It planted a question, it named the shape of something new, and it sent other researchers back to their own data to look for the same kind of signal. Meanwhile, on the other side of the Pacific, a different kind of instrument had been finding a different piece of the same puzzle. And the researcher holding it had no idea at first that what he was seeing was related to what Dragert had just found. Kazushige Obara was a seismologist at the National Research Institute for Earth Science and Disaster Resilience in Japan, NIED, and he was working with a network of sensors that were, in some ways, the mirror image of the GPS stations in the Pacific Northwest. Where GPS is sensitive to slow, quiet surface displacement, the HINET network, the High Sensitivity Seismograph Network of Japan, was designed to catch the smallest possible seismic vibrations, the faintest shaking, the most delicate motion of the ground. HINET consisted of hundreds of borehole seismometers, sensors installed not at the surface where traffic and wind and ocean waves clutter the record with noise, but buried hundreds of meters underground in boreholes drilled into bedrock, where the world is quieter. An instrument this sensitive, in a location this isolated from surface noise, can hear things that a surface seismometer misses entirely. And Obara, studying the records from stations in southwest Japan, positioned above the Nankai subduction zone, began noticing something in the data that did not fit any category he had a name for. The Nankai Trough is the great offshore trench where the Philippine Sea Plate dives beneath southwestern Japan, and it is one of the most geologically studied and most carefully watched subduction zones in the world, because Japan has been living alongside its potential consequences for a very long time. The Nankai has produced great earthquakes on a roughly century-scale cycle for as long as the historical record extends, magnitude 8 and magnitude 8. 5 events that have killed thousands, leveled cities, and sent tsunamis ashore. The monitoring infrastructure above it is accordingly dense and sophisticated, and HINET was part of that investment. And what Obara saw in the HINET records coming from stations positioned over the deep part of the Nankai interface was a persistent, low-amplitude seismic signal that could not be explained as ordinary tectonic noise. It was not the sharp, clear arrival of a normal earthquake. It had no beginning that could be precisely timed, no distinct P-wave arrival that a seismologist would use to say, the earthquake started here at this moment. Instead, it was a diffuse, rumbling signal, concentrated at low frequencies between roughly 1 and 10 Hz, frequencies that sit just at the lower edge of ordinary seismic detection. And it went on for minutes, sometimes hours, sometimes days. It looked, in the vocabulary of seismology, more like noise than like an earthquake. But it was organized noise, it was coherent across multiple stations, it came and went on what appeared to be a schedule, and it was coming from deep beneath the earth, from depths that matched not the shallow seismogenic zone where the great Nankai earthquakes nucleate, but the deeper transition zone, 40 or 50 kilometers below the surface, in a region that should, by the standard physics of subduction, be too hot and too plastic to generate any seismic signal at all. Obara published the discovery in Science in 2002, a year after Dragert's silent slip paper, and he named what he had found non-volcanic tremor. Seismic tremor not associated with any volcanic activity, not explainable by fluid injection from magma, arising instead from deep within a cold, subducting plate system. The term non-volcanic was important because tremor signals of certain kinds had been observed before in volcanic settings, where rising magma and hydrothermal fluids create characteristic harmonic signals in the crust. What Obara was seeing was something else, something tectonic, something related to the subduction process itself. But the mechanism was not yet clear, and the connection to the GPS reversal signal Dragert had documented in Cascadia was not yet made. Two research teams on opposite sides of the Pacific had, independently, found two different manifestations of what would turn out to be the same phenomenon. One watching the ground move slowly backwards with GPS, the other listening to an unfamiliar murmur in the deep rock with ultra-sensitive borehole sensors. Neither yet knew they were looking at the same thing. The link came 1 year later, and the person who made it was Garry Rogers. Rogers was a seismologist at the Geological Survey of Canada, the same institution where Dragert worked, and he had been studying the seismic records from arrays in the Pacific Northwest with a growing sense that something anomalous was present. Because around the same time the GPS stations were recording their strange westward reversals, the seismograph arrays were picking up a low-frequency, diffuse seismic signal in the tremor frequency range. Not the sharp arrivals of normal small earthquakes, but something extended and rumbling and without a clear origin time. The HyNet in Japan was not the only network sensitive enough to hear it. The seismograph arrays of the Pacific Northwest, if you knew what to look for, were catching it too. Rogers gathered the records from the seismic arrays in northern Washington and southern Vancouver Island and went looking for whether the two signals, the GPS reversal that Dragert had documented and the weak, low-frequency seismic noise he was now tracking, were happening at the same times in the same places. They were. The westward reversals in the GPS record, the silent slip of the deep fault, were accompanied each time by bursts of the strange, low-frequency tremor. The tremor arrived when the slip arrived and faded when the slip faded. The two signals were coupled. They were both expressions of the same underground event, seen through two completely different instruments, one measuring the slow surface displacement from weeks of quiet fault motion, the other catching the faint seismic murmur that accompanied that motion in the deep rock. Rogers and Dragert put this together and published the synthesis in Science in 2003. They gave the combined phenomenon a name that has stuck: Episodic Tremor and Slip, ETS, a single event with two observable faces, the silent GPS reversal that any seismometer would have missed, and the tremor that any GPS station would have missed. And only by having both kinds of instrument operating simultaneously in the same region had the thing become visible at all. The naming mattered because it defined a category, not just a curiosity, not just a local anomaly in one unusual subduction zone, but a repeating, structured phenomenon with its own characteristic signature, its own observable schedule, its own geographic coherence. Episodic tremor and slip. The word episodic, saying that it comes and goes in distinct episodes, not continuously. Tremor, naming the seismic vibration that is its audible face. And slip, naming the fault motion that is its physical heart. 3 words, and suddenly a field of research had its organizing concept, and researchers across the world had something to go looking for in their own data. And when they went looking, they found it. Japan had it. Obara's tremor turned out to be the seismic face of slow slip events that GPS arrays in southwest Japan confirmed were happening on the Nankai interface, and the Japanese monitoring community rapidly catalogued a whole menagerie of related events: short-term slow slip events lasting only a few days, long-term slow slip events lasting a year or more, and a class of signals called very low-frequency earthquakes, or VLF earthquakes, which were even slower than ordinary tremor, and sat at the deepest low-frequency end of the seismic spectrum, barely above the range detectable by standard seismographs. Cascadia had it, with a regularity that was by now beginning to seem almost clockwork. And other margins, as researchers went back to their archives, had versions of it too, hints and traces in old records that had never quite been explained and that in the light of ETS suddenly made sense. What had happened in the span of those 3 years between Dragert's 2001 paper and the wider recognition of ETS as a global phenomenon was something that geoscience does not always manage gracefully, but did here, a convergence of instruments and perspectives that together resolved a signal too subtle for any one of them to see alone. The GPS arrays had been there, recording ground position to millimeter precision, but without the tremor data to suggest that something was physically happening on the fault, the brief westward reversals could have been explained away as instrumental drift or atmospheric noise. The seismographs had been there, including the borehole sensors of HyNet, but without the GPS to show that the tremor corresponded to actual fault slip, it might have remained categorized as anomalous background noise of uncertain origin. Each dataset alone was suggestive but deniable. Together, the GPS and the tremor became irrefutable. The silent earthquake could be both measured and heard. It left 2 independent fingerprints in 2 independent instruments, and the only explanation for both fingerprints existing at the same place and the same time was a real, physical, repeating slip event on the deep fault. An event too slow for human senses, too slow for seismometers alone, too slow for any single instrument of the previous century, but perfectly legible to the conjunction of instruments that the late 20th century had, somewhat inadvertently, placed in just the right locations. There is something worth feeling in that on a quiet night when the mind is settling and the body is beginning to loosen. All those years, decades of the GPS stations blinking their positions up to the satellites and back, decades of seismometers scratching their continuous record onto drums and then into digital memory. All of it running in parallel, waiting, without knowing it was waiting, for the right person to look at both at once. The discovery was not a sudden revelation. It was patient. It was cumulative. It was built from the slow accumulation of millimeter measurements and from a researcher's willingness to wonder whether 2 strange signals arriving at the same time on different instruments might be 2 descriptions of the same invisible animal. And what the instruments were describing, the shape of the animal they had together finally caught, was this. Deep beneath the Pacific Northwest, at a depth of 30 to 45 kilometers or so below the surface of a landscape of fir trees and rain and small towns and ordinary lives, the Juan de Fuca plate was, on a schedule of roughly 14 months, quietly and briefly releasing some of the vast mechanical strain that the ongoing subduction had loaded onto the deep fault. Not suddenly, not violently, but persistently and in a way that left a clear mark on everything sensitive enough to notice. The ground reversed, the rock rumbled, and then weeks later it was over and the creep resumed and the spring began to wind again. The clockwork quality of this, the fact that it comes back roughly every 14 months, as if the deep fault has some internal timer, is one of the things that makes episodic tremor and slip, once you know about it, so difficult to stop thinking about. A fault that stores and releases stress on a predictable cycle does not behave like the earthquakes most people picture when they think of geological hazard. The ordinary model of earthquake occurrence is essentially random within broad statistical windows. The fault is locked, stress accumulates over decades or centuries, something eventually triggers failure, and the rupture happens whenever it happens, with no particular periodicity and very little advance warning. The great Cascadia earthquakes fit this model. The 1700 event was not announced on a schedule. It came when the locked zone finally failed, after what may have been centuries of accumulated loading. But ETS is different. ETS has a clock. The northern Cascadia segment beneath the Olympic Peninsula and southern Vancouver Island appears to run its silent earthquake cycle on something close to a 14-month period. Not perfectly. The interval varies somewhat between cycles, but regularly enough that researchers who have been watching the network for the past 2 decades can say, with reasonable confidence, roughly when the next episode is due, and then watch the GPS and the tremor arrays to see it arrive. Each time it arrives, it follows a pattern. It begins as a cluster of tremor in one part of the zone, often to the north or south at one end of the slip patch, and then it migrates. The slip does not happen all at once across the entire deep fault surface. Instead, the slipping zone moves. It propagates laterally along the fault at something between 5 and 15 kilometers per day. Think for a moment about what that means in concrete terms. The rupture front, the leading edge of the region that is actively slipping at any given moment, advances along the fault at a pace of roughly 5 to 15 kilometers every 24 hours. A brisk walk covers 5 kilometers in just over an hour. A slow drive through suburban traffic might cover 15 kilometers in 20 minutes. The thing that is, in energy terms, equivalent to a major earthquake, capable of releasing as much mechanical energy as a shock that would flatten buildings and rupture water mains, is advancing through the deep crust at a pace that a person on foot could, in principle, keep up with. If you could somehow walk at a steady pace along the surface above the migrating slip front, covering roughly a kilometer every 10 minutes or so through the forests and farms of western Washington, you would be staying abreast of an earthquake, one that no one around you could feel, one that the ground beneath your feet was completing in total silence, and at the end of 2 or 3 weeks it would be finished, and the fault would be still again, and the 14-month clock would begin winding toward the next one. The tremor migrates with the slip. As the slipping front advances along the fault, the zone of active tremor advances with it. Researchers tracking the HINET data in Japan and the seismic arrays in the Pacific Northwest have mapped this migration in detail, hour by hour in some studies, watching the tremor move along the deep fault at the walking pace that the slip prescribes. It is a strange image to hold, seismic noise advancing slowly through the rock of southwest Japan or through the deep plate boundary beneath Washington state, moving at the speed of a person walking, crossing hundreds of kilometers over the course of weeks, a slow, seismic wave of murmuring fault activity, audible only to the most sensitive borehole sensors buried hundreds of meters underground, invisible to every human sense, doing its patient work in the dark. But even calling it invisible is not quite accurate anymore, not since the instruments arrived, not since GPS learned to resolve millimeters, not since the HINET boreholes were drilled deep enough to hear below the noise floor of the surface world. What was invisible has become, in the technical sense, extraordinarily visible. The Cascadia ETS episodes are now monitored in near real time. When an episode begins, when the first tremor clusters appear on the seismic arrays and the first hints of the westward reversal show up in the GPS time series, the research community knows. There are people at the Pacific Northwest Seismic Network and at the Geological Survey of Canada watching for exactly this, tracking the tremor migration as it advances along the margin, comparing this episode's timing and extent to the 14-month cycle, noting which patches slipped this time and which did not, looking for anything unusual in the signature of an event that has, at this point, been observed dozens of times and has begun to yield its regularities. Regularity is not the same as predictability in the sense most people mean. The 14-month clock does not tell anyone when the next great Cascadia megathrust earthquake will occur. It says only when the next silent one will arrive. And even the silent one arrives with some variation around the average, sometimes 12 months after the last, sometimes 16, the periodicity consistent enough to be useful for planning and monitoring, but not so precise as to be a watch you could set. The deep fault has its own physics, its own fluid dynamics, its own sensitivity to conditions that change from cycle to cycle, and the regularity reflects underlying physical processes more than any simple mechanical timer. Why it returns on roughly the same schedule. Why the 14 months emerges as the characteristic interval for this segment of Cascadia, rather than 7 months or 3 years, is one of the questions the field is still working to answer. It has to do with the rate at which the fluid pressure on the deep fault recharges after a slip event drains it, and with the rate at which the ongoing subduction reloads the stress that each episode partially releases. But the details of those rates and their interplay in the deep crust of the Pacific Northwest are not yet fully resolved. The interval is observed. The mechanism that sets it is still, in the most precise sense, being worked out. And this is where the story of the discovery passes naturally into the story of the mechanism itself. Because knowing that the silent earthquakes exist and that they follow a clock, and that the clock can be read by GPS and tremor arrays, is only the beginning of understanding what they are. The instruments found the animal. Now comes the question of its biology. Why does the deep fault slip slowly and repeatedly instead of staying locked like the shallow zone above it? What is happening at 30 to 45 kilometers depth in the dark and the heat and the enormous pressure that makes this particular band of the plate boundary behave so differently from everything above and everything below? That question takes us into the rock itself, into the mineral physics of water under extreme pressure, into the temperature regime where stone begins to lose its brittleness without quite becoming fluid, into a world where the standard categories of solid and liquid, of locked and free, of quiet and active, all begin to blur at their edges, and where the blurring is not a failure of our descriptions, but a real property of the material, one that the Earth has been exploiting for a very long time to redistribute its stresses in ways that no seismometer, listening only for the sharpness of a sudden break, could ever have heard. And at the center of that world, the central character in the mechanism of the silent earthquake is not rock at all, it is water. Enormous quantities of water, chemically locked inside minerals, released slowly as the subducting plate descends and heats, migrating upward through the pores and microfractures of the deep crust into the fault zone itself, raising the fluid pressure there to levels that approach something called lithostatic pressure, a term meaning roughly the weight of all the rock above per unit area pressing down. When the pore fluid pressure on a fault approaches that level, something fundamental changes about how the fault can behave. And understanding what changes and why it produces the slow, rhythmic sliding of episodic tremor and slip rather than either locked silence or sudden rupture is the story the next part of this long, slow night wants to tell. But that explanation deserves its own unhurried space. The instruments have done their work. The discovery has been made step by careful step through millimeters of GPS motion and the faint murmur of borehole seismometers and the patient comparison of 2 data sets by 2 teams on opposite sides of the world who were, without quite knowing it, listening to the same deep thing. Herb Dragert saw the ground reverse. Kazushige Obara heard the tremor. Garry Rogers and Herb Dragert put both together and gave the thing its name. The silent earthquake had been found. And everything that came next, and the mechanism, the tidal sensitivity, the distant triggering, the question of what any of this tells us about the great ruptures still building, began from that moment of recognition. From the reading of a GPS time series on a winter morning in British Columbia, the line on the graph turning slowly, quietly, undeniably backward, a centimeter at a time. The rock below Vancouver Island had kept its secret for a very long time. It gave it up to millimeters. The fault, if you could somehow stand inside it, would be unrecognizable as a fault at all, not the dramatic open crack of a canyon wall, not the clean vertical face of a surface rupture still raw and white and sharp-edged. At the depth where episodic tremor and slip occurs, roughly 30 to 45 kilometers below the ground where people walk and sleep and go about their days, the rock has been compressed by the full weight of everything above it into something dense and dark and almost incomprehensible in its pressure. You would not see a gap. You would see two rock faces pressed together so firmly that the distinction between them is geological rather than visual, a boundary between one kind of stone and another kind of stone that the mind registers more as a transition than as a line. And yet something slides there, something moves slowly and rhythmically in a way that no one at the surface feels. And the question of why it does, why this particular depth, why this particular temperature, why here and not 10 kilometers shallower or 10 kilometers deeper, is one of the more beautiful questions in the whole long story of how the Earth behaves. The answer begins with temperature because temperature is the most fundamental controller of how rock deforms. Near the surface, rock is cold and brittle. Press it hard enough and fast enough and it breaks. That breaking is an ordinary earthquake, a sudden snap, a rupture that travels outward from a point, radiating the fast vibrations that seismometers were built to catch. But as you descend into the Earth, the temperature rises and rock changes its character. Deep enough and hot enough, the same minerals that would snap at the surface begin instead to flow slowly and permanently like a solid that has been granted over geological time a kind of patience. Below, somewhere around 500 degrees Celsius, in the deepest reaches of the subducting slab, the rock deforms without snapping at all. It creeps silently and continuously, too slowly and too deep for any of its motion to reach us as a vibration we could name. Between those two worlds, the brittle, snapping world above and the ductile, creeping world below, there is a transition. A zone where the temperature is neither cold enough for the rock to be purely brittle, nor hot enough for it to be purely ductile. A zone where the physical behavior of the interface becomes, in the language of the scientists who have studied it most carefully, conditionally stable, not locked, not freely sliding, something in between, something that can, under the right conditions, slip a little and stop, and then slip again, in a rhythm that takes weeks to complete and months to return. In the Cascadia subduction zone, that transition zone sits at roughly 30 to 45 kilometers of depth. The temperature there is somewhere in the range of 350 to 500 degrees Celsius. Not glowing, not molten, but warmer than any oven in any kitchen, warmer than anything a person would survive in for a fraction of a second. And that warmth is exactly what places the rocks there, in the narrow band of behavior where slow earthquakes become possible at all. Higher on the plate boundary, in the shallower locked zone above, the rock is colder and more brittle and stays stuck for centuries. Lower, in the deep, ductile roots of the subduction zone, the rock slides freely and silently without ever accumulating the kind of stress that could release as a quake of any kind. But in this middle layer, in this narrow window of temperature and depth, the fault can do something neither zone can do. It can slip slowly and then stop, and then slip again. But temperature alone does not explain the slow slip. Temperature sets the stage. What tips the fault into motion? What allows it to slide at all when the forces pressing the two plates together are so immense is fluid. Water in the deep earth does not look like water. It does not pool or trickle. It exists instead in the crystal lattices of minerals bound into the structure of the hydrous rocks that make up the cold subducting slab as it descends from the ocean floor into the mantle below, serpentinite, chlorite, amphibole. These are the minerals that carry water down, locked into their molecular architecture, as the Juan de Fuca plate dives beneath North America. And as the plate descends and the temperature and pressure rise, those minerals become unstable. They transform, shedding the water that was bound within them in a process called dehydration. The rock changes its composition, and the water that had been part of its structure is expelled, released into the surrounding rock, migrating upward and outward along whatever pathways the pressure and the geometry of the fault will allow. This released water accumulates on the fault interface, filling the microscopic pores and fractures in the rock at the plate boundary. And here is where the physics becomes, in the most precise sense, critical. The water in those pores is under pressure. Under the pressure of the rock above it, the same pressure that bears down on everything at that depth. But when the pore fluid pressure rises high enough, something remarkable happens to the fault's ability to resist sliding. There is a principle, foundational to the study of how rock fails, that the stress required to make a fault slip depends not just on the forces trying to push the two sides past each other, but also on how firmly the two sides are pressed together. The confining pressure, with the weight of the rock above, is what creates friction. Friction is what keeps the fault locked. And what pore fluid pressure does, when it rises high enough, is effectively push the two rock faces apart from within, reducing the friction between them, weakening the grip that has been holding the plates together. The term scientists use for the extreme case is near lithostatic pore fluid pressure. Lithostatic means, roughly, the pressure equivalent to the total weight of all the rock above a given point. It is the maximum pressure the weight of the crust can exert, per unit of area, at any given depth. When pore fluid pressure approaches that lithostatic value, the effective stress holding the fault faces together drops toward nearly nothing. The fault is no longer held firmly shut by the enormous weight of 30 kilometers of rock above it. It is, in a sense, floating, held together by almost nothing at all. And that is the condition that allows slow slip. Not enough fluid to cause the fault to rupture catastrophically in a sudden snap. The temperature window prevents that kind of brittle failure. But enough fluid at high enough pressure to reduce the grip between the plates to the point where the transition zone fault can slide slowly, releasing stress over days and weeks rather than seconds. The fluid is the lubricant that makes the slow earthquake possible. Without it, the transition zone would either remain stubbornly locked or creep too slowly and too quietly to produce even the tremor signal that eventually led to the discovery. And tremor is the next part of the story, because tremor is what the fluid-driven sliding produces as a byproduct. A faint, sustained acoustic signature of the slow motion itself, the sound, if you could call it that, of a fault sliding at a speed that generates no ordinary earthquake but still disturbs the rock enough to send a murmur upward through 30 kilometers of crust. Tectonic tremor looks nothing like an ordinary earthquake on a seismogram. A standard earthquake has a clear beginning, a sharp, sudden arrival of energy that even a trained eye can identify in an instant, a spike in the record that says, "Here, at this moment, the fault ruptured." Tremor has no such arrival. It begins gradually, almost imperceptibly, rising out of the background noise of the earth, the way a distant sound rises slowly into audibility when a room goes quiet. It lasts not for seconds, but for minutes, sometimes hours. Its energy is concentrated in the low-frequency range, roughly 1 to 10 cycles per second, slower and deeper pitched than the high-frequency snap of a brittle fracture. And it has no clear end either. It fades back into the noise from which it came, leaving the record of it looking less like an earthquake and more like a long, low, irregular vibration that drifted in and drifted out, leaving only a trace on the most sensitive instruments available. This is why seismologists missed it for so long. The instruments they had were calibrated for the thing they had always been looking for: the sudden onset, the sharp pulse the clear signal of a fault that had broken. Tremor, with its slow arrival and low frequency and long duration, looked too much like noise, too much like wind or ocean waves, or the distant rumble of traffic and machinery that contaminates every seismogram ever recorded near a human settlement. Without the HyNet borehole network in Japan, sensors sunk deep into the ground to isolate them from surface noise close enough to the source to catch the faint, low-frequency murmur, the tremor signal would have remained buried in the background for years longer than it did. The instruments had to be designed for a different purpose before the signal could be distinguished from the noise, and that distinction, once made, opened the entire field. What Kazushige Obara heard in the HyNet data beneath southwest Japan was a persistent, low-frequency vibration emanating from the deep interface of the Nankai subduction zone, not volcanic in origin, not related to any magma or hydrothermal system, but tectonic. The word he used was deep non-volcanic tremor, and it was the right description. The tremor came from the fault interface itself, from the slow sliding of one plate past another in the transition zone, and it was quiet enough that it had spent decades passing unnoticed through every seismometer ever deployed in that region without anyone knowing what it was. When that finding was combined with what Garry Rogers and Herb Dragert had seen in the GPS data from Cascadia, the slow-motion reversal of surface motion that accompanied bursts of exactly this kind of tremor, the picture became both clearer and more strange. The GPS ground moved, the seismometers murmured, and both happened together on a schedule. That schedule is one of the more quietly remarkable things about the whole phenomenon. Beneath the Olympic Peninsula of Washington State and the southern end of Vancouver Island, the pattern has been measured and documented across multiple cycles now. Every 14 months or so, not always on exactly the same calendar date, but close enough that the recurrence is unmistakable, the fault in the transition zone begins to slip. The tremor intensifies from background murmur to something detectable across many stations simultaneously. The GPS instruments on the surface above begin to record the faint but measurable signature of the ground moving in a direction contrary to its long-term trend. And for roughly 2 to 3 weeks, the event continues, gradually propagating along the fault in a way that is entirely unlike the instantaneous rupture of a great earthquake. Because the slip during an ETS episode does not begin everywhere at once, it begins in one place. One segment of the transition zone where the conditions are right, the fluid pressure high enough, the stress accumulated enough, and then it spreads. It migrates laterally along the fault, moving along the strike of the Cascadia subduction zone, northward or southward, at a rate of somewhere between 5 and 15 kilometers per day. Think for a moment about that speed, 5 to 15 kilometers per day. A brisk walk covers perhaps 5 kilometers in an hour. That means the rupture front of this earthquake, if you want to call it a rupture, though it is nothing like any rupture that would produce shaking, advances at roughly the pace of a person walking over the course of a day. In a week, it has moved perhaps 50 kilometers. In 2 weeks, 100. The fault is propagating, but at human speed, at the speed of daily life rather than the speed of sound. And over those 2 to 3 weeks, the total amount of energy released by this slow migration of slip accumulates into something genuinely large. A single ETS episode beneath the northern Cascadia segment can release seismic moment equivalent to a magnitude 6.5 earthquake. 6.5, that is not a trivial number. An M6.5 earthquake, if it released its energy in the conventional instantaneous way, would be felt strongly across a wide region. It would damage unreinforced structures. It would appear on the front pages of newspapers in any city within its reach. The 2014 South Napa earthquake, which caused hundreds of millions of dollars in damage and was felt across a large part of Northern California, was a magnitude 6. The Northridge earthquake of 1994, which killed dozens of people and caused billions in damage, was a magnitude 6.7. The energy contained in a single Cascadia ETS episode is on that order. Released in 2 to 3 weeks through a slow, silent migration of fault, slip across a patch of rock 30 to 45 kilometers underground, producing not a single tremor strong enough to wake a sleeping child, not a crack in a wall, not a rattle of dishes, not a moment of felt ground motion. The energy is real, the slip is real. The stress changes on the fault are real and measurable and consequential. But the signal it produces at the surface is a faint murmur in a borehole seismometer and a 2-centimeter kink in a GPS time series. And then quiet again for another 14 months. The 14-month recurrence itself deserves a moment of attention because it is not simply a curiosity, it is a constraint on the mechanism. For an event to recur on something approaching a regular schedule, 2 things must be true simultaneously. First, the stress that drives the slip must accumulate at a roughly predictable rate, which it does because the long-term convergence of the Juan de Fuca plate beneath North America happens at a roughly constant rate, loading the fault more or less continuously and more or less steadily, adding a small increment of strain to the transition zone with each passing year. Second, the threshold for slip must reset after each episode, the fluid pressure must rebuild, the stress on the fault must reload, the conditions must return to something close enough to what they were before that the same patch, at the same approximate interval, reaches the same approximate state and begins to slide again. This is why the ETS rhythm, while not perfectly metronomic, holds as well as it does. The process that drives it, the dehydration of the subducting slab, the slow accumulation of plate boundary stress, the gradual rebuilding of near lithostatic fluid pressure in the transition zone, operates on timescales of months to years, producing a cycle that is slow enough to be measurable and regular enough to be anticipated. The Northern Cascadia ETS recurrence of approximately 14 months is now documented well enough that researchers can look at the calendar and say, with reasonable confidence, that the next episode is approaching. Not to the day, but within a window of weeks. It is one of the few periodic behaviors in earthquake science reliable enough to allow that kind of prospective statement. And this is where the scaling law enters the picture, because the regularities of slow earthquakes turn out to encode something deep about their physical nature, something that sets them apart from ordinary earthquakes in a way that goes beyond the obvious difference of speed and sensation. For ordinary earthquakes, there is a well-established relationship between the size of an earthquake and the duration of its rupture. Large earthquakes last longer than small ones, and the relationship between their seismic moment, a measure of the total energy of the rupture, accounting for the area that slipped, the amount of slip, and the stiffness of the rock, and their duration follows a particular mathematical form. The seismic moment scales with the cube of the duration. An earthquake that lasts twice as long as another doesn't release twice the energy, it releases 8 times as much. This cubic relationship holds across a remarkable range of earthquake sizes, from tiny micro-earthquakes that last a fraction of a second to great megathrust earthquakes that rupture for several minutes, and its consistency across that range is one of the foundational regularities of seismology. Slow earthquakes do not follow this law. This was established in a study published in the journal Nature in 2007 by Shinji Aidi, Gregory Barroza, David Shelley, and Takahiko Uchide, who compiled data on slow slip events, tectonic tremor, and very low-frequency earthquakes from Cascadia and Japan, and looked at how their seismic moment related to their duration. What they found was that for slow earthquakes, the relationship is fundamentally different. The moment scales roughly linearly with duration, proportionally 1 to 1 rather than as the cube. An event that lasts twice as long releases roughly twice the energy, not 8 times, 2 times. This is not a small difference in a constant. It is a different scaling law, a different mathematical relationship between energy and duration, and it has physical meaning. For ordinary earthquakes, the cubic scaling arises because as a rupture grows, both the area of the fault that has slipped and the speed at which the rupture front propagates tend to increase together, compounding the energy released in a way that outpaces the simple proportionality. For slow earthquakes, this compounding doesn't happen. The rupture front advances slowly enough that the process is essentially rate-limited, constrained by the fluid pressure, by the temperature-dependent properties of the rock, by the balance of forces in the transition zone, and the energy release stays proportional to the time elapsed. The implication, which NIED and his co-authors drew out carefully, is that slow earthquakes are not simply ordinary earthquakes that happen to move slowly. They are a distinct category of fault motion, governed by their own physics, occupying their own region of the space of possible fault behaviors. They form, in the language the paper used, a unified family, a family that includes tectonic tremor, slow slip events, and very low-frequency earthquakes as related members, all obeying the same linear scaling, all products of the same transition zone environment where fluid pressure and temperature and confining stress conspire to produce motion that is neither the sudden snap of a brittle fracture nor the silent creep of the deep ductile zone. Very low-frequency earthquakes, in particular, are worth naming here. They are another member of the slow earthquake family, identified most thoroughly in Japan's Nankai subduction zone, and they occupy a position on the spectrum between ordinary small earthquakes and the broad envelope of slow slip events. Their duration is longer than an ordinary small quake, tens of seconds rather than a fraction of a second, and their energy is concentrated at frequencies even lower than tectonic tremor, below 1 cycle per second, in the range where the most sensitive seismometers operating in the quietest environments can barely distinguish them from the background. They are, in a sense, the faintest whisper in the slow earthquake family, audible only to the most attentive instruments in the quietest places. But they are there. They exist on the same fault in the same temperature and depth window at the same time as the slow slip events and the tremor, and they obey the same linear scaling law that identifies the whole family as something distinct from the violent world of ordinary seismicity. Japan has become, for reasons that are partly geological and partly instrumental, the best monitored laboratory for this whole family of slow events. The HyNet borehole network, which Kazushige Obara used to identify deep, non-volcanic tremor in 2002, is part of a broader national instrumentation effort that has placed sensitive sensors across the Japanese islands at a density that is probably unmatched anywhere else in the world. The Nankai subduction zone, which runs along the southern coast of Japan and poses one of the most serious earthquake and tsunami hazards on Earth, is the site where all 3 major types of slow events, short-term SSEs lasting days, long-term SSEs lasting months to over a year, and very low-frequency earthquakes have been documented and studied in the greatest detail. The geometry of the Nankai margin, the rate of convergence of the Philippine Sea Plate with Eurasia, and the properties of the subducted slab all conspire to make it a particularly active, slow earthquake environment, and the density of monitoring has made it possible to map the slow slip activity in ways that are simply not yet achievable elsewhere. But Japan and Cascadia are not the only places. Slow earthquakes and tectonic tremor have been found in subduction zones around the Pacific Rim and beyond, in Mexico, in Costa Rica, in Chile, in Alaska, in the Hikurangi margin off New Zealand. They have been found in places that are not subduction zones at all. The San Andreas Fault near Parkfield in central California shows tectonic tremor and slow slip behavior along segments of the fault at depth. The San Andreas is not a subduction zone. It is a transform fault where two plates slide past each other horizontally rather than one diving beneath the other. And yet, the transition zone conditions of temperature and fluid pressure and confining stress that produce slow earthquakes in the subduction world can apparently exist there too, at least in certain segments. The phenomenon is not a subduction trick. It is a consequence of particular physical conditions in the Earth's crust, and wherever those conditions exist, wherever a fault lies in the right temperature window, under the right fluid pressure, at the right depth, the slow earthquake can occur. This is a genuinely important point, and worth sitting with for a moment. For the first few years after the Cascadia and Nankai discoveries, it was tempting to think of slow earthquakes as a peculiarity of subduction zones, a behavior specific to the geometry of one plate diving beneath another. But the Parkfield tremor and the accumulating observations from other fault systems have shifted that picture. What defines a slow earthquake is not the geometry of the plate boundary, but the conditions on the fault interface, the temperature window, the fluid pressure, the balance between brittle failure and ductile creep. Those conditions can exist in many places, and where they exist, the slow earthquake can happen. The Cascadia and Nankai examples were discovered first because they are large, because the slow slip events there release substantial energy, and because they happen to sit beneath regions with good instrument coverage. But they may not be exceptional. They may be examples of something that is happening quietly and unobserved on faults around the world wherever the right conditions are present at depth. And the thing that is happening slowly, rhythmically, without felt motion in the dark rock below is not without consequence for the world above it. The transition zone where slow earthquakes occur does not exist in geological isolation. It sits directly below the locked seismogenic zone, the upper part of the plate boundary, where the plates are truly stuck, where the fault has been accumulating stress without releasing it, building toward the great rupture that will eventually come. The slow earthquakes in the transition zone and the locked zone above it are not independent systems. They are parts of the same fault at different depths with different behaviors, but coupled to each other by the stress field that runs through the rock, connecting them. Every ETS episode, every slow slip event in the transition zone redistributes stress on the fault system as a whole. The slip in the transition zone reduces the stress there because the fault has moved and released some of the accumulated strain. But the plate boundary doesn't stop at the bottom of the transition zone. The stress field extends upward into the locked zone above, and the redistribution that comes with each slow slip event transfers a small increment of that stress upward onto the locked patch. Not enough to trigger an immediate rupture. The locked zone has been accumulating stress for centuries, and one ETS episode contributes only a tiny fraction to the total load. But the transfer is real, and it is measurable, and it is not negligible over the long timescales that matter for great megathrust earthquakes. This is the connection that gives the slow earthquake its largest significance. The fault that will eventually produce the next great Cascadia earthquake, the same fault that tore loose on January 26, 1700, dropping the coastline of the Pacific Northwest into the sea and sending a tsunami across the Pacific to be recorded as an inexplicable wave with no local source in Japanese coastal village records that survived 3 centuries. That fault is being loaded, partially and incrementally, by each passing ETS cycle. 14 months go by, the transition zone slips. The stress on the locked zone increases by a small and measurable amount. 14 more months go by, the cycle repeats. The locked zone is, in this sense, listening to the transition zone below it, not in any metaphorical way, but in the precise mechanical sense that the stress field coupling them means that what happens in one influences the state of the other. How many cycles have there been since 1700? The interval between great Cascadia earthquakes is estimated from the geological record of buried coastlines and offshore turbidites. the layers of sediment shaken loose from the continental slope by strong shaking, to average several hundred years, ranging from roughly 200 to over 500 years, depending on the segment of the margin. The northern segment, which includes the area beneath Vancouver Island and the Olympic Peninsula where the ETS signal is best documented, has historically had longer intervals between great ruptures, sometimes exceeding 500 years. If the last event was in 1700 and the next could come anywhere in a range of 200 to 500 or more years from that date, then the window of time we are currently in encompasses everything from possibly already overdue to not due for centuries yet. No one can say with certainty which end of that range applies. What can be said is that the fault has been loading since 1700, and that each ETS cycle has been adding its small increment to that load, and that the process is ongoing, patient, and geologically indifferent to the schedule of human concern. Researchers have described the ETS episodes in terms of their effect on great earthquake probability carefully, because the language of probability in earthquake science is easy to misread. What the evidence supports is a modest elevation of hazard during and shortly after an ETS episode, because the stress transfer onto the locked zone reaches its maximum in that window, and because the locked zone is, in principle, somewhat closer to failure then than it was before the episode began. This is not the same as saying that an ETS episode is a countdown to a great earthquake. Most ETS episodes are followed by nothing. The locked zone absorbs the additional stress without rupturing, and 14 months later, the cycle begins again. The elevation in probability during an ETS window is real but small, and it does not translate to a predictable timeline or a specific warning. The science is careful to make this distinction, and the distinction matters because the gap between marginally elevated probability during a known stress transfer window and the big one is coming this month is the gap between calibrated understanding and something that is not understanding at all. What the ETS record does provide is a window, not a prediction, but a window into the mechanical state of a fault system that would otherwise be entirely opaque to observation. Before GPS, before continuous borehole seismometers, before the HyNet network and the Plate Boundary Observatory, the Cascadia subduction zone was essentially silent above the threshold of detection. Great earthquakes happened, and then centuries passed, and the fault loaded in darkness. Now the loading is no longer invisible. Every 14 months, the transition zone speaks, in millimeters of GPS displacement, in low-frequency murmur through borehole sensors. And what it says, decoded carefully by people like Herb Dragert and Garry Rogers and Kazushige Obara and the researchers who followed them, is a faint but legible account of the state of the fault, not a prediction, but a reading. A way of knowing something about where the system stands that was simply unavailable before these instruments existed and before anyone understood what they were hearing. The locked zone above the transition zone cannot speak in the same way. It is too cold, too brittle, too firmly stuck to produce the rhythmic slow-slip signal that makes ETS detectable. Its silence is a different kind of silence. Not the slow exhalation of a fault releasing stress incrementally, but the held breath of a fault that has not moved in more than 3 centuries and is still accumulating, still building, still waiting for the moment when the accumulated stress exceeds the friction holding it in place. That moment, when it comes, will not be slow. It will not be a 2-week migration of slip at a walking pace. It will be a rupture propagating at kilometers per second, releasing in minutes what has been stored in the rock since before the oldest city on the Pacific Northwest coast was built. That is the nature of the seismogenic zone, and nothing about the slow earthquakes in the transition zone below it changes what will eventually happen there. But for now, in the rhythm of the present, the transition zone continues its patient work. Roughly every 14 months, somewhere in the depth and darkness below the Olympic Peninsula and Vancouver Island and the southern coast of British Columbia, the conditions converge again. The fluid pressure, rebuilt in the 14 months since the last episode, approaches the near lithostatic threshold. The stress on the fault, reloaded by the continuing convergence of the Juan de Fuca plate, climbs back toward the level at which the transition zone can slip. And then, in some patch of rock at 30 to 45 kilometers of depth, at a temperature somewhere between 350 and 500 degrees Celsius, the fault begins to move, slowly, silently, migrating at the speed of a walking person along the strike of the margin, releasing the energy equivalent of a major earthquake over the course of 2 to 3 weeks and producing, as its only audible trace, a low, sustained, barely detectable murmur in the instruments of the people who have learned to listen for it. Above, on the surface, nothing. A clear night or a rainy one. Trees standing, buildings standing, people sleeping, entirely unaware that the ground 30 kilometers below them has just completed another cycle in a rhythm it has been keeping since long before anyone was alive to notice it. And yet, as still as the surface appears during those 2 or 3 weeks of silent motion, the fault is not simply indifferent to the world around it, it is listening. This is one of the stranger discoveries to have emerged from the long study of slow earthquakes, and it takes a moment to settle into the mind properly. The locked portion of a fault, the part that will eventually snap and produce a great earthquake, is held in place by enormous frictional forces, by the weight of mountains and ocean above it, by the interlocking grain of the rock itself. It is, in a sense, closed to the rest of the world. It does not respond to small things. But the transition zone, with its near lithostatic fluid pressure and its perpetual state of near failure, is another matter entirely. That fault is not closed, it is exquisitely, almost impossibly, open to the faintest outside influence. And one of the most faint and most constant influences on any point on the Earth's surface is the gravitational pull of the Moon and the Sun. You know the effect as the tides. The ocean rises and falls with it twice a day as the Moon's gravity draws the water of the sea toward it, and the Earth rotates underneath. But the ocean is not the only thing the Moon pulls. The solid rock of the Earth itself flexes under that force, deforming by centimeters as the gravitational gradient of the Moon sweeps across it. We call this the solid Earth tide, and it is real and measurable as slow, twice-daily breathing of the crust itself that passes through granite and basalt and compressed sediment as readily as it passes through water. The solid Earth tide changes the stress on every fault in the crust by a tiny amount, a few thousandths of a bar, a quantity so small that for most faults it is entirely lost in the noise of everything else going on. For a fault locked far from failure, it is nothing, a whisper in a thunderstorm. But the transition zone is not far from failure. It is, in the language used by researchers who study it, critically stressed, perpetually balanced at the very edge of the conditions required for slip. The fluid pressure has pushed the effective stress so low, and the accumulated tectonic load has pushed the shear stress so high that only the thinnest margin separates the current state from motion. And in that condition, a few thousandths of a bar is not nothing. It is enough. The pull of the Moon, waxing and waning across the face of the Earth twice a day, is sufficient to perceptibly modulate the rate of tectonic tremor beneath Cascadia and beneath southwest Japan's Nankai subduction zone. When the tidal stress on the fault nudges in the direction that favors slip, tremor intensifies. When it nudges in the opposite direction, tremor quiets. The Moon is not causing the slow earthquakes, but it is, in a very real sense, conducting them, adjusting the tempo of something already in motion, the way a hand on a pendulum can regulate a clock that is already swinging. This tidal sensitivity is not a curiosity, it is a diagnostic. It tells you something important about the physical state of the fault, something you could not easily learn any other way. A fault that responds to tidal stresses is a fault that is so close to failure that ordinary forces, not just the slow accumulation of tectonic convergence over decades, but the twice-daily rhythm of the Moon's pull, can measurably alter its behavior. It is, in the most literal sense, on the edge. And when researchers first demonstrated this cleanly by correlating tremor catalogues with the calculated tidal stress on the fault plane, at each moment the tremor occurred, it changed the way the field thought about what the transition zone was doing. It was not just slipping and stopping, it was continuously sampling the full stress environment around it, including forces most people would never think of as geological. The ocean tide itself adds another layer. The weight of seawater above an offshore fault changes with the tide, loading and unloading the crust, and that loading also slightly modulates tremor in coastal subduction zones. So the fault beneath southern Vancouver Island, 30 to 45 kilometers down, registers the passage of the ocean tide above it. It registers the pull of the Moon. It is, in a quiet way, more aware of the world than almost any other piece of rock in the crust because it has no margin to spare. And then there is a third kind of influence, stranger still and more dramatic. In November of 2002, a large earthquake struck in the wilderness of interior Alaska. The Denali Fault, a long continental strike-slip fault running through the heart of the state, ruptured over a length of more than 300 kilometers, producing a magnitude 7.9 earthquake, one of the largest to occur on American soil in decades. It was devastating in its own right, though its remote location spared it from causing a large human death toll. The energy released by that rupture spread outward as seismic waves in every direction, and those waves, the long, slow surface waves that travel around the entire planet after a great earthquake, arrived minutes later at fault systems far away. They were still measurable at seismograph stations thousands of kilometers from the epicenter, and as they passed through the Pacific Northwest, those waves triggered bursts of tectonic tremor on the Cascadia subduction zone. Think about what that means for a moment. A fault in Alaska, tearing through rock at the speed of kilometers per second, sends out a ripple. That ripple crosses the Gulf of Alaska and sweeps through British Columbia and Washington, and as it passes, the transition zone of the Cascadia subduction zone, 30 to 45 kilometers below the surface, responds. Not with a great earthquake, not with anything a person could feel, but with a burst of tremor, a measurable intensification of the low-frequency murmur in the instruments. The Alaskan rupture did not cause a Cascadia earthquake, but it woke the tremor, briefly, as if jostling something already balanced at the edge of motion. 2 years later, on the day after Christmas in 2004, the largest earthquake in the world in nearly 40 years struck off the northwest coast of Sumatra. The Sumatra Andaman earthquake registered a magnitude of 9.1, rupturing a length of fault that stretched roughly 1,200 kilometers and generating the tsunami that would kill more than 200,000 people across the Indian Ocean basin. The surface waves from that earthquake were so powerful that they set the entire Earth ringing like a struck bell, oscillating in its normal modes for days afterward, and those waves, sweeping around the planet and across the Pacific, triggered tremor bursts on fault systems as far away as Cascadia and the Nankai subduction zone in Japan. The Sumatra earthquake was on the other side of the world, and still the transition zone felt it. This remote triggering of tremor by distant great earthquakes has now been documented at multiple sites and for multiple events, and it consistently demonstrates the same underlying truth. The fault in the transition zone, already laden with near lithostatic fluid pressure, already stressed to within a thin margin of slip, responds to stress changes that are orders of magnitude smaller than anything that would affect a normal, well-locked fault. The seismic waves from Alaska or Sumatra do not bring enough stress to unlock a fault held tight by tectonic forces, but they are enough to perturb a fault already on the edge. They are enough to rattle a door that is almost open. There is something in this that is, once you sit with it, both deeply strange and strangely peaceful. The Earth, at those depths, is not isolated from itself. A tremor recorded in Japan may be faintly answering an earthquake in Chile. A fault in the Pacific Northwest may stir briefly in response to a rupture beneath the Indian Ocean. The crust is a connected body, and the slow earthquakes, precisely because they live at the threshold of motion, are among the most sensitive readers of that connection. They are, in a sense, the nervous system of the plate boundary, not the dramatic signal of a great rupture, but the constant, quiet sensitivity that registers even the faintest passing stress. And the family of slow events is, it turns out, broader than any single description can contain. When researchers first began cataloguing what they were finding on the Nankai subduction zone beneath southwest Japan, using the dense, high-net borehole network that Kazushige Obara and his colleagues at NIED had deployed across the Japanese islands, they found not a single type of slow event, but a whole population of them ranging across timescales in ways that no one had initially expected. There were short-term slow slip events lasting only a few days in the shallow part of the subduction interface, the fault near the trench, near the seafloor. There were long-term slow slip events persisting for months or longer in the deeper transition zone. There were the tremors arriving in concert with the GPS-measured slip, lasting minutes to hours in their individual bursts. And there was a fourth type christened very low-frequency earthquakes, or VLF earthquakes, events with a seismic signature intermediate between ordinary earthquakes and tremor, too slow and too low in frequency to be called a normal quake, too sharply defined to be called tremor. They seemed to occur at the shallowest portion of the slow slip zone, closest to the locked, potentially tsunami-genic section of the fault. The picture that emerged was of a spectrum, not a binary. At one end, the ordinary earthquakes of the seismogenic zone, fast, sharp, violent, the fault snapping in seconds. At the other end, simple aseismic creep, the fault sliding so slowly and steadily that it never accumulates enough strain to release anything at all, just a quiet, constant glide. And between those two extremes, a rich and continuous family of intermediate behaviors, the VLF earthquakes, the tremors, the short-term slow slip events, the long-term slow slip events, all governed by physics subtly different from ordinary earthquakes, all connected to the fluid-saturated near-failure transition zone, and all together constituting a distinct mode of fault behavior that the seismology of the 20th century had been, quite literally, unable to see. The 2007 Nature paper by Shinji Ide, Gregory Baroza, David Shelley, and Takahiko Uchide helped bring this spectrum into formal focus. They were examining how the energy released by slow earthquakes scales with their duration. How much seismic moment does a slow event release, and how does that scale as the events get longer? For ordinary earthquakes, the answer follows a well-known cubic relationship. Double the duration, and you get roughly 8 times the seismic moment. This is the signature of a rupture propagating at a speed set by the elastic properties of the rock, a crack that grows as fast as stress can drive it, bounded only by friction and the dimensions of the fault. But slow earthquakes, when Ide, Baroza, Shelley and Uchide examined them across a range of timescales and magnitudes, did not follow the cubic law. Their seismic moment scaled roughly linearly with duration. Double the duration and you get roughly double the moment, a much shallower relationship reflecting a very different physics. The slow earthquake does not accelerate as it grows. It does not drive itself faster. It creeps at a pace set by the fluid pressure and the temperature and the detailed friction of the rock in its particular zone, and it releases energy in proportion to the time it spends moving, not in proportion to the cube of that time. This was not merely a mathematical observation. It meant that slow earthquakes are not simply ordinary earthquakes that happen to be slow. They are a different type of fault motion, governed by different physics, occupying a different part of the parameter space that describes how faults can behave. And it meant that the boundary between slow and fast was not sharp. The family of fault behaviors was continuous, running from the VLF earthquakes through the tremors, through the slow slip events, through something eventually that begins to look more and more like an ordinary earthquake, depending on the temperature, the depth, the fluid pressure, the mineralogy, the exact frictional properties of the rock on that patch of fault on that day. The transition zone, then, is not simply a curiosity between a locked fault above and a sliding fault below. It is a laboratory running continuously in which the full range of intermediate fault behaviors is being expressed, measured, and, increasingly, understood. And the slow earthquakes are not confined to subduction zones. In central California, near the small town of Parkfield, the San Andreas Fault has been one of the most intensively studied faults on Earth for decades. Parkfield sits at a peculiar point along the San Andreas, the boundary between the locked, earthquake-producing section of the fault to the south and the freely creeping section to the north, where the fault slips steadily without accumulating elastic strain. It is a natural transition zone, and researchers have drilled into it, monitored it with seismometers and strain meters and GPS and borehole sensors, and watched it produce a series of moderate earthquakes that once seemed to follow a roughly regular schedule. What those instruments also found, particularly in the years following the installation of the deep borehole monitoring network, was tectonic tremor. Not from a subduction zone, not from the meeting of an oceanic plate and a continental one, but from the San Andreas itself. A continental strike-slip fault where two pieces of the same continent grind horizontally past each other. The tremor near Parkfield occurs at depths of about 15 to 30 kilometers, in a setting quite different from the Cascadia or Nankai subduction interface. But it has many of the same characteristics. Low frequency, no clear onset, associated with slow slip, sensitive to small stress perturbations. This matters because it means the fluid-rich, near-failure transition zone capable of producing slow earthquakes is not a peculiarity of ocean plate subduction. It is a feature that can arise wherever the right combination of temperature, depth, fluid, and mineralogy comes together on a fault. The conditions that produce slow earthquakes are not narrow and exotic. They are, in the broadest sense, a general consequence of how rock behaves in the middle crust when fluid is present, when temperature is in a certain range, and when the fault is loaded close to failure. The San Andreas, the most famous fault in North America, is producing them, and where the San Andreas produces them, so might other faults that have not yet been monitored carefully enough to notice. How many slow earthquakes have rolled through the Earth in the decades and centuries before GPS could see them? How many ETS episodes cycled through beneath the Olympic Peninsula, loading the locked zone incrementally, while the people above slept in their houses and felt nothing and had no instrument that could have told them anything was happening? There is no way to know. The GPS record goes back only a few decades. The HyNet borehole network in Japan was deployed only in the late 1990s. The slow earthquakes were always there. The physics that produces them did not begin when the instruments arrived. But the history of those episodes, the centuries of 14-month cycles beneath Cascadia, the equivalent slow rhythms beneath the Nankai trough, is largely invisible to us, accessible only by inference, by analogy, by the understanding of what the physics requires. And this invisibility bears on the most consequential question the slow earthquakes raise. In the early hours of March 11, 2011, the sea floor off the coast of Tohoku, on the Pacific coast of northern Honshu, Japan, ruptured. The Tohoku Oki earthquake, registering a magnitude of 9.0, tore open a patch of the Japan Trench subduction zone roughly 400 kilometers long and 200 kilometers wide, displacing the ocean floor by many meters in a matter of minutes and generating a tsunami that swept inland across the coastal plain of northeast Japan, with consequences that need no elaboration here. It was, by almost any measure, the most powerful earthquake ever recorded on Japanese soil, and it was the fourth largest earthquake ever measured anywhere on Earth. In the months that followed, as researchers began the work of understanding not just what had happened, but how, one of the questions that drew close attention was what had been happening in the weeks and months before. And the answer, when it came, was both illuminating and sobering. A paper published in Science in 2012 by Eitaro Kato and his colleagues documented what the dense seismic and geodetic networks of Japan had recorded before the main shock. There had been a foreshock sequence, a series of moderate earthquakes in the weeks preceding March 11th that had attracted attention at the time but had not been recognized as a warning. And beneath that foreshock sequence, there had been slow slip, migrating, quiet, GPS-visible deformation that had been advancing up-dip toward the eventual rupture area in the weeks before the great earthquake struck. The slow slip and the migrating foreshocks were moving together, a slow front of stress redistribution creeping toward the place where the fault would eventually tear. This was not, to be absolutely clear, a prediction that went unheeded. No one in early 2011 had in real time recognized that sequence as a precursor to a magnitude 9. The slow slip was within the range of variation that geodetic networks observed routinely. The foreshocks, though they were noted, looked, in the moment, like the kind of activity that often does not precede anything more significant. The science of distinguishing between a slow slip sequence that will be followed by a great earthquake and one that will simply end quietly was not, in 2011, anywhere near mature enough to have made that call. It is not, in 2025, mature enough to make it reliably. But the Kato 2012 study, once the retrospective analysis was complete, showed that the precursor had been there. Slow deformation, advancing toward the eventual hypocenter in the weeks before the largest earthquake in Japanese recorded history. The fault had, in some sense, been whispering. 2.5 years later, on April 1, 2014, a magnitude 8.2 earthquake struck off the coast of Iquique in northern Chile. The Iquique earthquake was itself preceded by a documented slow slip event and a migrating foreshock sequence that GPS and seismic networks had recorded in the weeks before. Sergio Ruiz and his colleagues, publishing in Science in 2014, showed the sequence clearly: the slow deformation, the foreshocks migrating toward the eventual rupture area, and then the great earthquake breaking through. Here, as at Tohoku, the slow slip had been part of the story of nucleation. The way the fault had warmed up, redistributed stress, and prepared the conditions for the main shock to occur. Two great earthquakes, both preceded by documented slow slip and foreshock sequences, both retrospectively clear, neither recognized in real time as a warning. This combination of retrospective clarity and real-time blindness is where the science currently lives, and it is important to understand what it does and does not mean. It does not mean that slow slip events are precursors to great earthquakes. Most slow slip events, the overwhelming majority of Cascadia ETS episodes, the regular cycles beneath the Nankai trough, the tremor sequences that researchers now track in near real time, most of them are followed by nothing. The 14-month cycle beneath the Olympic Peninsula rolls through and ends, and the next great Cascadia earthquake does not come. It will come eventually. The physics of the subduction zone and the history of the 1700 rupture make that certain as anything in geology can be. But the relationship between any individual ETS episode and the timing of that eventual rupture is not deterministic. The slow earthquake transfers a small increment of stress to the locked zone. It modestly, marginally, raises the probability of a great earthquake during and shortly after the episode. The probability goes up slightly when ETS is active, it comes back down when ETS ends. But slightly elevated is not imminent, and a slightly elevated probability, starting from an already low baseline, remains a low probability in absolute terms. The honest answer to the question of whether slow slip events can predict great earthquakes is this: they are part of the process. They have been present before some great earthquakes. They are not present before all of them. And we cannot yet tell, in real time, the difference between an SSE sequence that is loading toward a main shock and one that will simply end quietly in 2 or 3 weeks, as dozens of previous episodes have. The science is genuine, the mechanisms are real, the connection to hazard is real, and the prediction is not yet within reach. What is within reach is monitoring and understanding and the slow accumulation of the kind of knowledge that might, eventually, allow the distinction to be made. The networks, the Plate Boundary Observatory's GPS stations across the Pacific Northwest, the high-net borehole sensors beneath Japan, the Chilean geodetic network that recorded Iquique's precursor, are running continuously. The algorithms that process their data are improving. The catalogues of slow events are growing longer, decade by decade, and with longer catalogues and better physics, the science moves quietly but inexorably towards something it cannot yet do. In the meantime, beneath the Cascadia subduction zone, the transition zone continues its cycle. The next ETS episode will come, as it always does, somewhere around 14 months after the last one, give or take the variation that the fault's own complexity introduces. The GPS stations across Vancouver Island and the Olympic Peninsula and the coast of Washington will register it. The brief westward reversal of the long-term eastward motion, the millimeter-scale kink in the time series, the unmistakable signature of the ground that is not moving the way it was moving yesterday. The borehole strain meters will feel the changing stress. The seismic arrays will pick up the tremor. The low, sustained, barely there rumble in the 1 to 10 Hertz band, migrating southward or northward along the margin at the pace of a person walking. Researchers will note the time and the location and the magnitude of the slip. They will add it to the catalogue. And the transition zone, having completed another cycle of its patient, persistent, invisible work, will begin reloading. Above, on the surface, the same nothing. Houses standing, trees standing, the same roads, the same cities on the coast, the same people sleeping through the night without the faintest indication that anything at all has passed through the ground beneath their beds. There is a way of thinking about this that is calming, and there is a way of thinking about it that is not, and the truth is that both ways are true simultaneously. The calming version is this: the Earth is not volatile or unpredictable in the way that a panicked imagination might suggest. The transition zone's 14-month cycle is a rhythm, and rhythms are the opposite of chaos. The fault is doing something regular and lawful, something that can be measured and tracked and understood. The slow earthquakes are not signs of impending disaster in any immediate sense. They are signs that the planet is doing what it has always done, redistributing stress, balancing forces, expressing in quiet motion the physics of two plates converging at a few centimeters per year. The ETS episodes are part of the normal operation of the subduction zone, the steady background process by which the margin accommodates the convergence that the locked zone above is temporarily refusing to accommodate. They are, in a sense, the planet's way of keeping things in balance without violence, at least for now, at least in this zone, at least for another 14 months. And the ominous version, the one that hums quietly beneath the calming one, is simply that the locked zone exists, that it has been accumulating strain for 325 years since the last great rupture, that it will eventually release that strain in an earthquake that will be felt across the entire Pacific Northwest, and that will send a tsunami into the Pacific, and that will be, when it comes, one of the most consequential natural events in the recorded history of North America. The slow earthquakes do not change that, they do not prevent it, they do not accelerate it perceptibly. They simply continue patient and rhythmic and silent, transferring their small increments of stress to the locked zone one episode at a time, keeping the company of the moon and the sun and the passing waves of distant earthquakes, while the great store of elastic energy in the seismogenic zone above them waits for its moment in geological time. These two truths do not cancel each other. They coexist the way the surface of the Pacific Ocean can be calm and still and beautiful on a night when the deep water below it is moving in currents that traverse the entire ocean basin. The surface is exactly as calm as it looks. The deep is exactly as large as it is. Both are true. And there is something in the very invisibility of the slow earthquakes that speaks to this. The planet has been doing this work for as long as the Cascadia subduction zone has existed. For millions of years, through all of geological time, the transition zone slipping and reloading and slipping again in its slow rhythm while nothing on the surface gave any indication. The 14-month cycle did not begin when Herb Dragert first published the GPS data in 2001. It was there before the first GPS satellite was launched, before the first seismograph was built, before the first human being stood on the coast of what would someday be called the Pacific Northwest and watched the ocean. The slow earthquakes are ancient, we are new, and it is only in the last few decades of our brief, instrument-equipped existence on this coast that we have gained the faint and partial ability to hear them at all. That the moon's gravity is enough to modulate their rhythm, that the surface waves of a great earthquake in Sumatra can be felt in the deep rock beneath Vancouver Island, that a rupture in Alaska can stir the transition zone of Cascadia, that the slow creak of the fault can be read in the GPS record with millimeter precision from instruments bolted to the rock at the surface. All of this, the tidal sensitivity, the remote triggering, the spectrum of slow events from VLF earthquakes to long-term SSEs, the Parkfield tremor on the San Andreas, the Tohoku and Ikiki precursors, the 14-month Cascadia clockwork, all of it has been learned within a single human lifetime, within the working careers of Herb Dragert, Garry Rogers, Kazushige Obara, Shinji Aide, Gregory Barossa, David Shelley, and the hundreds of researchers who have built on their work. The field of slow earthquake science is, in geological terms, younger than an infant. And yet it has already revealed something that changes the way you might imagine the ground beneath you. Not as passive, not as inert, not as the simply solid and unmoving thing that everyday experience suggests, but as a body engaged in continuous, complex, patient motion at depths that daily life never touches, motion that responds to the moon, motion that listens to earthquakes on the other side of the planet, motion that transfers stress, loads faults, migrates along margins at walking pace, and leaves its signature in the faint, reverse kink of a GPS time series. A millimeter or two, a week or two, a few centimeters of ground that briefly forgot to move in the direction it had been moving for decades and slipped quietly the other way. The slow earthquakes are the ground breathing, slowly, deeply on a time scale that no individual human life is long enough to fully witness. A single 14-month cycle is long enough to be nearly invisible in the course of a year, and yet short enough that a researcher who has spent 20 years at a monitoring station has watched it more than a dozen times. It is the rhythm, beneath the daily tides, beneath the seasonal weather, beneath the human generations who have lived and died on the coast above it, the fault doing its slow and patient work, keeping its own time. Tonight, somewhere in the depth below Vancouver Island or the Olympic Peninsula or the coast of Northern California, the transition zone is in some phase of its cycle. It may be in the quiet period of reloading, the fluid pressure slowly rebuilding in the weeks or months since the last episode, the stress climbing incrementally back toward the threshold. It may be in the early hours of a new episode, the slip just beginning to initiate on some small patch of fault deep in the dark, the tremor just beginning to appear in the instruments of the researchers who are watching. It may be migrating, the slow rupture front advancing along the margin at 5 to 15 kilometers per day, carrying its low-frequency murmur with it, the GPS stations along the coast registering one by one the brief reversal of their long-term motion as the slip passes beneath them. You cannot feel it. No one can feel it. There is no instrument that a person carries in their body that is sensitive enough to register the motion, no sense that reports the change in the rock 30 to 45 kilometers below the surface. The birds outside are still, the branches are still. The water in a glass on a nightstand does not tremble. Everything that a person can observe from the surface is exactly as quiet as it appears. And yet the ground is moving. If you feel drawn to share where in the world you are resting tonight, what coast or city or countryside sits above the particular piece of crust that is your portion of the earth, I would genuinely like to know. The comments are there, and I read them. There is something fitting about knowing where the people are who have spent this night listening to the slow, deep pulse of the planet. There are more stories here of the same slow and careful kind, waiting for whenever you want them. But for now, let the rock below you be what it is, ancient and patient and quietly in motion, doing its unhurried work in the dark, as it has done for all the time before you arrived and will do for all the time after. The fault has its rhythm. The moon has its pull. The instruments have their vigil. And you have done enough for one night. Put down whatever remains of the day. Tie off here at the wisdom docks. The tide will wait till morning.